So the purpose of this, and it's a talk, I like to do quite long decks. It's more of a discussion. This is a fair train of thought from me, but it's based on a lot of the thinking I've been doing over the last 5 or 6 years. And thank you very much to Vince Cerf for setting me up on this one, because I've heard him say this several times before. If we don't get applications to work, then we're all having a lot of fun, but it's not particularly useful. The critical question is, how do we provide internet services to other planets? And when I say internet services, I'm talking about the applications and that kind of stuff. So I'm just going to digress into an anecdote. About 10 years ago, I went to a fascinating technical presentation on information-centric networking. And they were doing some incredibly clever things with distributed hash tabling and a whole unique way of addressing based on probabilistic forwarding. And it was fascinating. And in the Q&A afterwards, somebody put their hand up and said, how do we make this work with the internet? And their answer was, well, you rewrite the internet. And that can't be our answer. Bundle protocol is really smart. A DTN solves so many problems in space, but we cannot just rewrite the internet. We have to have compatibility. So the question should really be, how do we provide internet services to other planets without having to rewrite everything? And that's what I'm going to hope to address. So really, we have three possible approaches. Number one, we use bundle protocol end-to-end. It's great, it works. Number two, we use IP end-to-end. Well, we've got IP, we've spent 50 years working out how to make IP work. Why not use it? And number three is, well, we could use IP and BP as the transport protocols that underpin whatever applications are doing on top of it and use it where appropriate. So what I'll do is I'm just going to go through each of these in turn. And the last one, quick spoiler, I'm going to go into a lot more detail. So step one, BP end-to-end. Well, this works. You know, this is what is currently being planned, and Felix has talked about what ESA are doing, and NASA are doing likewise, and commercial people are doing the same sort of thing. When you need something which is particularly a space protocol, it is something engineered for the operations of your spacecraft, for your particular science mission, bundle protocol is great. And when it's a bespoke protocol, it's probably the right choice. It should be your first choice. But we can't rewrite everything, because not everything is a special space protocol. But I'll call that a success, and then we'll move on to IP end-to-end. So the problem with IP end-to-end, and I don't want to rehash this too much, there is a lot of material out there about this, TCP/IP does not work over space links. Come talk to me about congestion, drops, time windows, etc. There's lots to discuss there. And University of Bologna and Carlo Caini's team have got some great results underpinning this with proper science. Second point, IP optimized for space links starts to look an awful lot like bundle protocol with a different header format. Once you start saying, oh, we won't have congestion, and oh, we'll put some extra option blocks in there for how long I should store it, and oh, we probably need some clock information. It's just BPv7 with an IPv6 frame format. Don't think you're solving your problem. Third point, putting IP in BP, it's inefficient because you're double wrapping. And also it just hides the TCP/IP problem. You're putting IP frames in bundles. There's a reason you're doing that, because you've got something running over that IP, and whatever's running over that IP is probably TCP or QUIC. And then you've just hidden the problem. You've still got that congestion control problem, and your protocol's not going to work, because that applies to QUIC as well, is the key point. So I'm going to put a red line through that and say, don't do that. Okay? So number three, let's use IP and BP as transport. So, I mean, why not use both IP and BP where they work best? So, quick digression into the OC network stack. I'm sure you all know all about this. And first off, I've put a red line through the presentation there because nobody knows what it is. And it's not a perfect model. But the key point here is bundle protocol and IP live at 3 and 4. They're the network layer, they're the transport layer. It's all to do with routing and moving data. Users and developers and applications live way at the top of the stack. They actually shouldn't care how their data is getting moved around as long as it meets their guarantees. They care about that top layer. And all those engineers who write those applications that people actually care and use about, you care and use, care about 5 and 7. So the billion-dollar question, and I think I use the word billion advisedly if we're looking 20, 30 years ahead, can we preserve the end-to-end application protocol semantics as defined at layer 5 and 7, but change the transport protocols, the 3 and 4, hop by hop? And can we do it without modifying the first and last hop? And that's quite a key point, because if we can avoid modifying the hop from the source to wherever, and the hop from the -1 to the end, then those can be the existing internet service applications that we know and love, web, email, blah, blah, blah. So a lot of people, and this is not a unique idea from me, this is a summary of a lot of the conversations that are happening at the moment, is perhaps some kind of application layer gateway might help. When I talk about an application layer gateway, I mean either some variation of that, where a client has an application layer protocol communication with a server somewhere, and we're assuming these are over interplanetary distances. But what's actually happening is that client is having an IP conversation with a gateway. The gateway is then having a BP conversation with another gateway. And that gateway is sending it back into IP, making the request to the server, and the reverse path goes the other way. The other option is some variation of caching. So the client makes a request to the application layer gateway over IP, no change required. That nearby application layer gateway has some content already because it's been dribbled down over time across a BP network from some terrestrial upstream server that knows to push out news headlines of the day, sports results, weather, I don't know. And so the client can use what is always used, but is actually accessing cached content. So that's very much how content delivery networks work at the moment. That's actually how Netflix works. There isn't a Netflix server. It's the one at the end of your road. So the next question is, what actually runs on the internet? And getting this data is hard, and these are estimates, but I think they're pretty accurate. So based on total protocol traffic, so this is kind of counting IP datagrams, 75 to 85% of it is web API stuff. It's HTTP, gRPC, insert name of your favorite HTTP variant here, but it's all basically web and REST. Below that, there's a bit of peer-to-peer and file sharing stuff that's still going on. Not hugely popular, but terribly chatty, which is why ISPs hate it, by the way. Then there's gaming and real-time services. It's kind of everyone's playing Fortnite or whatever. Okay, so that's 2 to 5%. Only, 5% optimistically. Email is fascinating. Email is estimated to be less than 1% of total internet traffic. That's to the credit of the email protocols. That's billions of emails being sent, but it consumes very little bandwidth. Very nicely done. Well done, those guys. And then the bottom 15% is the core background infrastructure maintenance stuff, DNS, people doing SSH and all that kind of other unclassified BGP stuff, whatever. So let's put some red lines through things we don't care about. Don't care about file sharing. Nobody's going to be running peer-to-peer networks between here and the moon. There's not going to be students, so forget it. Gaming in real time, sorry, you are not playing Fortnite with your mates on the moon. It's just not going to happen. I don't care. I'm also going to put a line through SSH and unclassified, because anything which requires an interactive round trip, you might just about make it work onto the moon, but anywhere beyond that, it's not viable, and I'm just not going to talk about it. Set someone else up to try and talk about real-time interactive sessions over DTN distances, go for it. I don't want to touch that, thank you. So we're going to look at these things for the purposes of today. So having scratched all the other things, that just kind of leaves us with them and some others. So, Facebook, Netflix, Spotify, all those applications that the entire internet consumes, including Snapchat and whatever else. I'm not saying anyone is going to run TikTok on the moon. But the underlying protocol services that all of those applications that generate billions of dollars on Earth, they're doing it on protocols that we need to be able to support because that's what engineers know and love. And if we can't support the things that those services use, then we're going back to rewriting the internet again. So, quick bit of analysis. I gave you those two variations. One, which was the end-to-end, where you do an IP hop, a BP hop, and an IP hop. I'll call that the end-to-end path. And the other one was the cached variant. So very scruffy matrix. HTTP works end-to-end? Yeah, sure. So this is an analysis of the underlying, of the current protocol and the way it is architected. HTTP understands the nature of a cache. That's how proxying works. That's how CDNs work. HTTP understands that. But also HTTP works end-to-end. RTP, comparable. End-to-end, you're thinking more kind of real-time communication, Zoom style stuff. Possibly not relevant for us, but worth having on here. SMTP is content cached anyway. It's relaying, it's hop by hop, you know. DNS as well. And I'll touch more on DNS at the end, so don't get too excited that I'm glossing over it. So, caching and proxying actually require the same capability. And this goes back to my earlier question of, can we maintain the semantics and content of the application protocol and change the underlying protocol? So in both of the use cases of when you're caching something nearby so that applications can access it, and when you're actually doing that end-to-end, you still need to understand what the application cares about, package it and move it either in advance or on demand. So, and this is a slightly artistic diagram. It's not entirely accurate. Please don't pick holes in it. But it does demonstrate one thing, which is over time, all four of these, these big major application protocols have suffered from transport specialization, as I'm kind of calling it, where people have said, oh, I kind of like the idea that it's a general way of moving stuff, but I have to run on the internet. I have to run over an MTU of, let's say, 1400, 1500 on a good day. So I've got to start packing things into frames. So RTP, for example, has this lovely concept of streams of video and streams of audio, but then you chunk them into network allocation units. I can't even remember what NALU stands for. Go read RTP, it's fascinating. Into the RTP framing format, let's put some more headers on it, which bangs onto UDP, which then goes onto IP. So you'll see that the funnel forces, the tail is wagging the dog in all of these examples. Assumptions at the high layer are being influenced by the fact that fundamentally they've got to run it over IP. Not a terrible idea. HTTP, great. We have REST, we have HTTPS, runs over TLS, which runs over TCP. It's reliable, it's streaming, works beautifully. But unpicking it gets a bit complicated. And trying to work out where in these nicely pastel shaded stacks we can draw that line and say, this is application semantics, and everything below is transport semantics, so we can make a nice clean cut. It gets a bit tricky. Good news. I should be doing a Jeremy Clarkson impression, sorry. Good news. We are not the only community trying to unpick these application protocols. It doesn't just have to be us, the DTN community. The quick people want to do the same thing because they have quick, and quick is provably better in a number of cases on the terrestrial internet. It makes good money for the big internet providers. And so they're porting all the applications that used to run over TCP and UDP to run over quick, which means they are doing that unpicking, that picking where the slice point in the stacks are. And because they are big and well-funded, they can go out to the original designers of the original protocols and say, help us. You wrote this. Help us unpick this so that we can port it. So yeah, let's largely steal what they've done, where it's appropriate, and repurpose it for our own use. So I'll go through these now. Starting with HTTP. Good news, RFC 9110 already defines what we need. So it talks about what is a hypertext transfer protocol request and response. What are the role of headers? What headers talk about content? What headers are actually transport flags? How do we cache these things? What is the role of an intermediate? It's a really good RFC. If anyone wants to do a takeaway of things they should read this week, go read 9110. It's a really well-written document by the people who built HTTP. You know, Mark Nottingham's name's on it. It's good stuff. With everything that is written in that good document, we can say, now we can clearly understand what we should put inside a bundle that we may have to reformat to suit the fact that it's going in a bundle, but we can understand the semantics that we can transfer transparently from an HTTP 1.1 or an HTTP 3 session. We can understand what a request is. We can translate it into a different format to travel across a BP hop, and we can unpack it without losing the semantics, because we understand what the semantics are. So the request that hits the far end server, having transited across multiple transports, has not lost valuable information that the originator put in there. And that's the key point of being able to transfer the semantics. And it lets us build both of the examples we were talking about, the cached ones on the bottom, the end-to-end ones on the top. So we can take an HTTP request that came in over IP, the ALG can understand what the actual semantics of that request were, push it across BP, turn it back into IP, it hits the server without losing the information, the response can flow back. Of course, there's a round trip time here. We may need a new status code for HTTP, which says your response is going to take a while, but everything you've done is correct and you haven't made a mistake. A kind of 100 code, let's call it 104, nice. And equally, the cached thing works quite nicely. So HTTP understands about caching. There's a whole lot of stuff in there about caching control within HTTP requests. All of that just works. And most of that behavior is already pre-described in 9110. So we can copy it. But this breaks end-to-end security. I can see why I'm nodding. Yeah, I know it does. But we know how to do that, because we already do this in corporate environments. If you've ever worked for a large company, you'll discover that the office proxy or the corporate proxy is already intercepting all your HTTPS traffic. And there's some tricks. Actually, I've got a very rich slide coming up, which explains exactly how they do it. And I assert that for now, all other planets are just corporate environments. If you are being sent to stand on the moon, then you're going to trust the space agency certificate on your local server. If you don't, I think there are wider problems. So if there is trust in the gateway, then the gateway can intercept, it can do the whole wildcarding SSL thing. This is a well-known process. And as I say, if you don't trust the gateway, then you've got a rebellion on another planet. And I think we've got wider problems than certificate mistrust. So I'll show these slides afterwards. Read this at your heart's content. I'm not going to force you to parse all that text. But this is a well-known technique that is deployed everywhere. Quick aside, having talked about HTTP, CoAP. Not a lot of people know about CoAP, but CoAP is a big deal in the IoT world. So the guys behind CoAP looked at using HTTP for very small power-constrained devices, looked at it and went, oh, we don't really want a full TCP stack. Can we do something light over UDP and IP? And Carsten Bormann and associates, who are very, very smart cookies, unpicked the semantics of REST and rebuilt a really nice CBOR-based IoT protocol. And Carlos Gomez and his team are already pushing forwards a proposal to run CoAP natively over BP. We don't even need to do that while they're doing the work, which is great. And it's a good fit, and it's happening. So the whole IoT request response system, that's just going to happen over BP. No extra work for us. I will include Carlos in us, so lots of good work by Carlos. Next, audio video, multimedia. Traditionally RTP, but I'm trying to broaden the specification. So again, it's the quick guys. So there's a media over quick IETF working group who have taken it upon themselves to refactor the whole RTP stack in order to make it run really efficiently over quick. And what they've done, bless them, is they've taken a step back, a total look at the way effectively systems like Netflix, big content delivery systems for rich multimedia with multiple languages and subtitles and audio tracks and all of this stuff is delivered at global internet scale with minimal latency. What I didn't realize is when you watch iTunes, even when it's interactive, Apple TV, there is something like a 5-minute delay that's coming down, and that's because of the way they manage all that content delivery. So Quick are pretty much trying to reduce that. We don't really care. But what's really interesting is they have rethought the way you package and discuss and talk about the semantics of multimedia. So video with associated subtitles, with different language translations of the audio. How do you talk about that in generic terms, separate from, and how do you compress and do smart things at the sort of codec layer, separate from, and now how do we move them? And we can reuse most of that work because they've got this really nice logical packaging model. It's not an RFC yet. It's on about revision 14 of the draft in the mock group, but it's well worth consulting because that's directly reusable. So we can take one of their packages of a short snippet of multimedia, we can put it in a bundle and we can ship it through and say, this is the next piece because it has all that interrelation to allow the receiving client to stitch it all back together in the right order and handle out of all reception, blah, blah. They fixed that. Well, they say they fixed it. They put the work in. So, you know, no need for us to do that again. So the key point is, tick. It's reusable for us and it supports all the codecs. So we don't need to go and play with the MP4 people again and the MPEG consortium and VP8 and without change. So that lets us build classic content delivery for multimedia. Key point on this slide is you'll notice there's actually 3 little application layer gateways. The one on the left isn't an ALG. The one on the left is something the mock people are developing. And that is a server that speaks mock on one side and speaks RTP on the other, because they need it to roll out mock. So in a terrestrial environment, they will already have those mock compliant servers that are pushing out RTP, et cetera, et cetera. So we don't even need to write that end. We just need to cover the orange bit in the middle. This is great. And the blue text is quite key here. This is for streaming content that has been cached and gathered somewhere. Not talking about making Zoom calls with this stuff. Distance, don't go there. It also enables this, and I'm going slightly off-piste here. If we worked out how to package multimedia in an elegant way that we can put it back together and make it run over bundles, then for those use cases where we don't need the whole IP world anymore, we just need audio video over bundle protocol, then why don't we just do this? Rather than trying to work out how to put RTP in bundles, which I know CCSDS has been looking at, and I'm not sure I think is the right idea. Because when you're trying to put IP inside bundles, trying to put RTP inside bundles, you're taking all those design decisions that RTP is optimized for as part of the baggage of putting it in bundle protocol. So all the reasons for making it 1500 bytes. And do I now put multiple RTP frames inside the bundles? You're stuck on RTP. Back away from it. I think its time is gone. What Mock are doing helps us sidestep the optimizations that RTP has made for the terrestrial internet and allows us to talk about multimedia. It's a side conversation, and I'm sure I'm going to get hate mail from Felix on this one, but I look forward to it. Next to the big 4, as I'm calling them, like a Safari, email. So email is already store and forward, and it works hop by hop. So job done. Yeah, well, almost. So the dirty secret about email is the existence of spam has killed hop by hop. If any of you ever tried to set up and run your own email systems at home, I decided that was a fun idea once. If your mail server is set up as an open relay, i.e. it does hop by hop in the same way that we would call a bundle processing agent as an open relay, you will be blacklisted by everyone who ever touches your server. And unpicking that blacklisting, speaking from experience, is annoying. So yeah, there is no hop to hop in email anymore. It goes from the sender's server to the recipient's server. Also, email's been around a while. It's still 7-bit ASCII, which means we're throwing away an eighth of our bandwidth. And parsing it is a pain, and let's not do that. And MIME, if you've looked at MIME, you can tell I've been looking at this quite recently. MIME is solving a problem entirely of SMTP's making. The problem with SMTP is that you've got all this stuff in text, and therefore you need some sort of text indicator to say where the different gaps are, and it also has this whole session concept where a server will dial and say, I've got a bunch of messages for you. Have you got any messages for me? And it's quite long pole like that. So we could specify a CBOR encoded envelope, which would wrap around a mail message quite nicely. That, instead of using ASCII in MIME, that'd be quite cute. We could develop a special well-known service ID and a BP protocol to be able to transfer messages forwards and back. That'd be cool. And then we can enforce security using BPSec, and then no more spam. And that could be even better. We don't even need to use that for space anymore. We can fix email globally. And if anyone wants to do it, go for it. I think it would be really cool. But it would let us build all of this stuff, SMTP done properly. But we can actually do this with SMTP and ASCII if we just say, oh, it's a bit more code and it's not 100% efficient. Perhaps that's good enough. Perhaps we probably shouldn't focus on email. If somebody really wants to, I'm not going to stand in their way, but I think there are higher priority tasks. Last, and I am getting there. Sorry, this is a long presentation. You've got to sit tight. DNS. Yeah, so DNS is decentralized and federated. So is it also job done? Yeah. But we could improve some of it. Zone transfers are a little bit tuned for TCP, some of the request response stuff. Yeah. So we could do a slightly better over BP encoding, but otherwise, DNS is pretty much done. I'm going to say one key thing about DNS. There is only one global DNS tree. DNS is built with the assumption that there is only one DNS and it holds everything. It's delegated and federated and extendable and so on, but there is only one DNS. You don't have an idea of, now I'm on another planet, I have a different DNS, and sometime halfway on the journey from A to B, I swap DNSs. That is alien to the entire way DNS is architected. And there's some details, no objection to a .luna top-level domain. That sounds great. In the same way that there's a .uk and a .com and there's even a .us, and I'm not sure who uses it, but it exists. That's great. Divide up the scope. That's fine. But there's only one DNS. If you look up Aalyria.com, you should get the Aalyria resource because it's owned by Aalyria. Just because you're on the moon, you can't squat on Aalyria or Google, for example. If you change those assumptions, we're going back to step one, rewrite the internet, because you're making a statement which is the whole way you do DNS resolution, which is critical for applications, is now different in space. Go rewrite the assumptions in your apps. It's a non-starter. But you can do some smart stuff so that you can know if you're on the moon that you want a different response. And it's called split horizon DNS, and it's a well-known technique. Again, it comes from the corporate world. If you're inside Google and try and access Gmail, you get a different server and a different service than when you walk out of the building on your mobile phone. It's a well-known way of doing it. It allows you to do slightly more structured responses based on where the request originator is. So on the moon, if someone tries to get, to Zoom, you can get a response to say not reachable from here. But as soon as they get home, the next response will be, yes, it is reachable. Or actually, you're going to see an ALG, not the end result, not for Zoom, of course, but for, BBC News. BBC News is going via a gateway, it's slightly out of date, or it's going all the way back to Earth expected delay. You can get those nuances of response by split horizon DNS. And it's not new, it's well understood, just requires config and the right servers. So, quick checkpoint. and then I'm about 2 minutes out, if that's okay. Quick checkpoint. Use BP end-to-end. Tick. Green. Lovely. 2. IP end-to-end. Please stand. 3. Use IP and BP as transport. Tick. Green. Lovely. What happens if we can do both 1 and 3? That would be really cool. But how do we decide which to use and when? What I mean by this is, let's say I've got a pretty smart end device built for the lunar environment, some kind of funky lunar laptop. And it has a stack which is native BP and a stack which is IP. So it's dual stacked, and it can do both. When I access, I don't know, my lunarweather.com, should I be using the BP way of doing it, because I can do that, or should I be using the IP way of doing it, because I can do that as well? And this is where the glorious RFC 9460 comes in. There's a concept called DNS service binding. It is pretty hot off the press. You can tell by the 9.4 start to the RFC. This has come in with the transfer from HTTP 2 to HTTP 3, and it adds a richness to DNS responses to say more than the IP address of the thing you want is over here. It says, the thing you have asked me for, the service you have asked me for, is not only over here, but you've got some choices. You could use this protocol or that protocol with these extra parameters to it. So for HTTP, it could be certificate information, and also some address hints, so you don't have to then do an immediate lookup. And that richness is really useful. And it's one of the things that my colleague Eric Klein is pushing really hard at the moment. And he's looking to add back into DNS as an extension of that service record. So we can start to add bundle protocol specific information in there. So you can, going back to my earlier example, do your DNS lookup for mylunarweather.com and get a response with service findings. It says priority 1, if you've got it, use bundle protocol. Here is the EID, the IPN address of the actual server which will serve you the content over our marvelous HTTP over BP that we've worked out how to do. Alternatively, here's the IP address, IPv4, IPv6, blah, 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 blah. Priority 1 or 2, please use BP. That service can then say, great, and make that choice dynamically. The second thing that is actively being worked on is that EID can be an IPN number. And then, of course, if you're living on the IP world still, you might want to work out how to resolve that IPN number back to an IP address so you can establish a TCP/CL or a UDP/CL conversation in order to start transferring the bundles. Because remember, in bits of the terrestrial internet, DTN is an overlay. So you need to work out the IP information in order to manage the overlay hops. And again, we can use DNS for that. And I think we're about 3 months away from having a .ipn.arpa. So that's at the same level as inadra.arpa and inat6.arpa. So there will be 3 address families in global DNS: bundle protocol IPN, IPv6, and IPv4. I think we should be quite proud of that if we can get that to work, because that means we've landed, we're a thing. And that allows a client to decide for itself, depending on where it is with split horizon DNS, and what its own capabilities are, and what its own policy is on whether it's going to use a native BP stack or an IP stack or some variation of the two. So, conclusion, there's actually a 4. Same 1, 2, and 3. 4, choose IP or BP as you wish. And then all the clients and servers and tools and libraries, developer knowledge, and all that investment in education and those Computer Science 101 courses just work as they always did. So I started with the question, how do we provide internet services to other planets? It's Vince's question, not really mine. My answer is build on what we already have. You don't need to rewrite the internet. With a few targeted enhancements, I propose that the architecture and protocols we have now will work for the foreseeable future. That's it. Thank you.
Thank you.